Hello, everyone. Welcome back to the next seminar. We're continuing to talk about the Yang-Mills equations. Vishnu has kindly agreed to spend today's seminar proving a result he stated last time. He tells me that it's quite difficult, and so we'll look forward to seeing what he has to come up with. Thank you, Vishnu.
Thanks, Tim. So I'm going to talk about this theorem I introduced last time, but maybe I'll just mention a reference that is useful if you want to go look at the full theorem and all the details. There's a book called, I just mentioned Uhlenbeck Compactness by Katrin Werheim. That has all the details. Most of the proofs, the original proof was done for vector bundles, but the proof of principal bundles is basically identical. But this it's just that the notation and the calculations for vector bundles are they are easier to read on paper, and for principal bundles sometimes it can be a bit confusing, which is what I found. Okay, so what was our goal? Our goal was to solve the Yang-Mills equations, but we had a big issue, which was that they weren't elliptic. So let's write down the Yang-Mills equations again. So we had 0 equals d star a. So when we have a manifold M, or we have a principal bundle P on M with group G and a connection one form. Okay, and then associated to the connection one form, we had the curvature two form, which was the exterior derivative of the connection one form. So, it was the covariant derivative of the connection one form. And then the Yang-Mills equations were just the adjoint of the code of the exterior covariant derivative applied to Fa equals 0. And we calculated that not in local coordinates, but written down expanded, we get d star d a plus a dA plus a comma a comma a is that's what it looks like. Okay, so the issue was that we had this term here, which is not an elliptic. The highest order term is not elliptic. If we had a d star a as well, then it would be elliptic because that's the same as the Hodge Laplacian, right? So then, this natural thing to guess was, can we transform this connection A so that it does satisfy d star a equals 0, which means this highest order term actually is elliptic. Yeah, so main issue was that, we have this equation, the Yang-Mills equations, are gauge invariant. Right? So to give another explanation as to why this is a problem for finding bounds on norms of A, if we have a gauge transformation, so I had this space which I called curly G. That was a space of gauge transformations of P, right? And those basically were these transformations that fix the fiber of the principal bundle and commute with multiplication by an element of the Lie group, right? Then this gauge invariance means that this dA star, okay, so it means that dA star Fa equals 0 implies that d of the pullback F also equals 0. Okay. So now, okay, so since we have this formula, Fa is equal to dA plus this bracket thing, then, so if let's say A is in, well, I'll just write A is in, like a natural space for A would be WP1, but I'm just going to choose N on 2, 1. Then, just looking at this equation, we can see that F is obtained by differentiating once. So you can say that FA is in Ln on 2. So, a question that you ask about, these kinds of operators is that is the converse true? But actually, this gauge invariance exactly says that that couldn't possibly be true, because, well, this norm, this F A P star of P, that's equal to integral over M of this quantity F A, comma F A to the okay P on 2, no, 2, let's just write one more step. So F A the P d mu, which is, yeah, P on 2, isn't it? Yeah. F A comma F A to the P on 2. Right? Now, when we apply a gauge transformation to A here, it turns out that this is equivalent to doing this. I mean, the gauge transformation doesn't affect this functional at all. So even if so like the curvature doesn't change at all, but you could make this gauge transformation, be very bad, like oscillate really rapidly, and so you could reasonably make A's p norm as large as you want, whilst F's p norm doesn't change. So you couldn't expect a converse inequality to be true. So that's why it's a good idea to fix a gauge in this problem. Yeah, okay, so this is the main theorem. I stated I think I stated a more general version of this before, but I'm going to stick to a simple version. So for 1 less than P less than N, yeah. Actually, it's true for P greater than 1, but I'm only going to say anything about P less than N. And in fact, for the general case, actually, P has to be greater than greater than or equal to N on 2 and less than N. There exist constants epsilon and c greater than 0, such that if A is a smooth connection over the unit ball with this N on 2 norm of F, bounded by epsilon, then you can find a gauge transformation. A gauge equivalent A hat with some nice properties. So A, well, it's in this gauge, Coulomb gauge. This is called the Coulomb gauge. It vanishes on the well, its normal derivative on its contraction with the normal vector to the boundary of the ball equals 0. And it has this property that we were looking for. I mean, it's not really necessary to put that A hat there because this quantity doesn't depend on gauge, is independent of gauge transformations. So yeah, so this is just this is actually the curvature of the original connection. Would be fine to do that. Okay, so this theorem is useful because you can just, if you have a a manifold, and you wanted to, you could restrict the balls for which this is true, and then make an argument to patch together those balls to find a global gauge transformation, and then uh, it turns out that this means that if you can couple the two equations, the Young-Mills equations plus this equation together to find, to get, regularity properties of solutions to Young-Mills equations. Okay, so we just need a couple of, technical theorems, which I won't prove. So first, we have the Sobolev-Emitting theorem. So if 1 on n plus 1 on r is greater than or equal to 1 on q, then A is less than or equal to C A 1 comma q. Okay, we just need that part of it, and then we also need this regularity. Well, I guess in this case it's just a D operator, but you can conclude this, I think, from the Hodge, looking at the Hodge Laplacian. So 1 less than P less than infinity if A is in W1P and A vanishes on the boundary, vanishes in the normal direction, then we get this A uh, 1 comma P is equal to C dA P plus D star A P. Okay, so those are the main two things that we'll need. This proof of various generalizations of this theorem is in that book.
Looks like we lost Vishnu again. Perhaps this is a repeat of last time. I guess we'll just give it a couple of minutes to see if he makes a nice comeback.
Sorry, I disconnected for some reason, just like last time, but fortunately I have someone here who is letting me know that it's messing up. Okay, let's see, share. Can people hear me now?
Yes, can hear you and see you.
Perfect, okay. Okay, so yeah, so I stated these two theorems, and now I want to try and prove these theorems. So Okay, so let's define these kinds of restricted and pullback operators, which is a connection. So a row, I'm going to call f row pullback under this map f row of a restricted to a ball of radius rho around the origin for row in 0, 1. Okay, and this map f row of x is just going to be rho x, right? So we're restricting to a smaller ball and then scaling up and then pulling back the restricted connection. Okay, so the argument is going to work. So I'm going to say let's let a u in 0, 1 be the set of connections. I guess set of row such that a row can be is gauge equivalent to a connection. So let's call it a row hat satisfying a to c. Okay, so these a to c, these three properties. So basically, it's just going to be, we're going to show that this set is open, closed, and non-empty, right? Right, so 1 is our original connection, so that proves the theorem. Okay, so, well, firstly, for non-empty, well, a row of some vector v, that's going to be a row v, which equals 0. Well, okay, let's write this. Yeah, well, so a0 equals 0. So 0 satisfies all these conditions. So we know it's non-empty. Now, I'm not going to say much about the closed one, except that, yeah, so suppose we have some sequence, row I to row with row I is in U, then, and suppose that, oh, well, yeah, that's part of the definition of U, isn't it? So, well, these three conditions, they're all closed conditions. So if I have a sequence, as long as it converges, then the limit will also satisfy these three conditions. Okay. So now assume that, now if we assume if we have a row I bounded in n on 2, 1 by some constant eta, then the limit will also satisfy this inequality. Well, actually, I want this, let me just put it like this for now. And the reason for that is because we have the sequence in Wn onto 1, and so it converges weakly. And then, but then by lower semi-continuity of norms, we can conclude that the limit also satisfies this inequality here. Okay, and yeah, so closed is slightly easier, I think. You can read a full argument in the book or in Uhlenbeck's original paper. But I want to spend most of my time on, well, yeah, then a row n on 2, 1 less than or equal to eta. So now I'll talk about openness mostly for the rest of the talk. Well, okay, there's definitely more to do here. You have to show that this limit, that the kind of sequence of gauge transformations also converges, and the limit actually gives you a gauge transformation that gives you something that's in Coulomb gauge, right? So the details of that are in the book. Okay, so openness. So this condition C is a closed condition. So what we're going to do is we're going to try and replace it with an open condition in order to, well, we're going to actually prove that it's an open condition actually, but let's try that. Let's do that like this follows. So assume that our norm A, n on 2 comma 1 is bounded by eta. And okay, so let me say it like this. Actually, I want to say, assume that, I'll write the same thing. N on 2 comma 1 is less than eta. For where I'm writing A equals A rho for some rho in U. Okay, so it does satisfy all these three properties, and I want to prove that, and I'm assuming this one. Actually, no, sorry, sorry, I said that quite a bit wrong. Let's assume that this is true and A and B hold. So this is an open condition, and I'm going to prove that this open condition implies this closed condition. And actually, I'm going to prove that these two conditions are equivalent. So our original condition part C is an open condition. Okay, so since FA, which is dA plus A bracket A, we can immediately get that dA in P is bounded by FA P plus A, which A bracket A P. So that theorem I mentioned before, the regularity theorem. Now we have d star A is equal to 0. So I'll just go up to show you that quickly. This one, we have d star A is equal to 0. So we can just ignore that term. So we just get that dA P norm bounds A1P. So so we get, so dA P is then other way around. So you get A1P is this then equal to C D dA P. Right, so then we get A1P, so that's equal to C norm of FA P plus this nonlinear term, which is kind of the problem term here. So we should try and control this term here. Okay, we can do some calculation, but this kind of looks like it's a product, so maybe we can use Holder's inequality, and actually we can do that. So I'll just quickly sketch out how we replace this kind of bracket with just a product of A's. So, I mean, mainly is if I have Lie algebra valued one forms, let's say xi comma mu, then if we look at this, the norm at a particular, like just the norm of these are one forms on vector spaces in a product, mu like this, and we write we write these structure constants I, j, k is this inner product here. Then this becomes I and mu j ei ej, and that's less than or equal to Cijk squared psi square xi I squared mu j squared. And so that's less than or equal to c times psi squared mu squared. So there's a c here, but actually there's two metric, there's a square, like there's two metrics here and only one metric here. So I could just scale the metric on the Lie algebra in order to make C1 or something, right? So what this tells me is that I can do this thing. Norm of A comma A squared P norm, that's equal to, well, okay, it's less than or equal to this thing here. Why have I put a squared P? Integral of B of A squared. Okay, so that's coming from this part goes to A squared, so A times A, so we get A to the 2P dx 1 on B. Okay, so basically that's equal to A 2P squared. 2P to the 2P. Right, yeah. Okay, so then I can write A, this is my previous, I'm going, yeah, this AP1 is controlled by C, FA, P plus A squared 2P. So it's still, I still have a problem. I have this quadratic term, not good. I can't move it to the other side yet. Okay, so now that we have this got rid of the brackets, we can now use Holder's inequality and apply to this thing. So A 2P squared less than or equal to A n times A.
Sorry, I don't remember my norms well
Sorry.
enough. I'd forgotten the definition of norms, but the third last line you corrected it to the 2p norm of A squared, and then you changed it back to 2p. I thought the squared looked right.
Oh yeah, you're right. Yeah, it is squared. Yeah. Yep, you're right. Yep. I just had it written slightly different in my notes, and when I was just adjusting it, I didn't do it correctly. Yeah, AQ, comma, yeah, AQ, where 1 on P plus 1 on N equal plus, well, 1 on P equals 1 on N plus 1 on Q. Yep. Okay, so then that splits this up once. But what I'm going to try and do is I want to get a P1 here so that I can move this to the other side. So we need to use the Sobolev inequality and apply to these two things. So they give, so well, I'm applying it separately to each one of these norms. So we get a Q is less than or equal to C, a P comma 1, which is nice, right? Because we used Holder's inequality here. And sorry, let me just, I think I've written something wrong here. Yeah, but don't my notes, I don't think I have this next part written quite right, but because of the way we chose Q here, it turns out that this is the exact way to get back to P. Right? And then A n is less than or equal to C A n on 2 comma 1. Which is good because we assumed an estimate on that already. Okay. Okay, so I'm just going to plug these in. And so putting that back into the equation, we get A, P comma 1 is less than or equal to C1 F A P plus C2 A P comma 1 times A n on 2 comma 1. Okay, so well now we select eta. So choose. Recall eta was this number that I assumed that this is bounded by. Okay, so eta, so that I want it to satisfy this. Eta C2 is less than a half. So now I can just take this, move it to the other side, and then move that constant to the other side, and I get, well, I'll just write it down. I get 1 on 2, A P comma 1 is less than or equal to C F A P. So we get kind of back 3, C. Okay, so we get back from assuming this this condition, this open condition, we get back. Where is it? Yeah, we get back our original condition. Okay, and actually conversely, well, yeah. So conversely, if we set P equals n on 2 and epsilon to be less than n divided by, okay, so if I set P equals n on 2, I get A n on 2 comma 1 less than or equal to C, or so I've proven that A, B, the first two conditions plus this third condition, which was that this third open condition, it implies the C, right? Now, if I have A, B, and C, I want to show that it implies this open condition. Well, that's much easier. Or it's kind of just by the definition. N on 2 less than C epsilon. And so choose epsilon to be equal to eta on C. So we get the right thing here. Okay, so now it says that if I have a limit, actually, if I have a connection that satisfies C of A, B, and C, then it also satisfies this condition for nearby rows as well. So now the next part of the openness condition is actually trying to solve the first two conditions, right? Once you have this control in part C. Yeah, I'm not going to go through the full that full argument, but I'll kind of sketch it out here, like the rest of the argument. So like what we're trying to do now is show that if rho is in U, then rho plus epsilon is in U. Okay, so let's write a rho plus epsilon as a rho plus some one form lambda, the algebra valued one form lambda. Okay, so now what we want to do is if lambda is small enough, we want to prove that we can solve the equation for a gauge transformation. Okay. So this whole time I've been talking about solving this gauge transformation equation, and I haven't actually written it down once, what the equation is. And I did that purposefully because I didn't really want to write it down because it's kind of, I at least find it a bit confusing, the form of the equation. So I'm going to write it down, but I'm not going to say much about it, except for that the kind of overall method we use to solve this equation for nearby connections. Okay, so for lambda, let's say small. Okay, so so locally, we can write like some open neighborhood V in M. We can write a gauge transformation phi of P as like the P times a map. So this, oh sorry, yeah, as this thing where sigma is some kind of smooth map into the Lie group. I'm not that confident with exactly this stuff, but I'm still going to write it down. Then if you write what the local equation for the gauge transformation is in terms of sigma, we get that dA hat of a section is equal to sigma dA hat sigma S. Well, actually, I guess the way I'm writing it here, I'm kind of I'm not real quite, I think it's not exactly correct to write it this way for principal bundles. So for vector bundles, it's kind of written like this. And that is equal to D plus sigma inverse A sigma plus sigma inverse D sigma applied to S. So if S was a section of a vector bundle and sigma was a map to the structure group of that vector bundle, you could see this, and you would, you had taken a local coordinates in which your vector bundle was just something cross Rn. Then this sigma is just a matrix here. So this D sigma is a Lie algebra valued one form, right? So I think that kind of is what's happening here. So then, the transformed thing here, A hat, is sigma inverse A sigma plus sigma inverse D sigma.
So I'm a little bit confused about the third line back. Is that one of those supposed to be a S prime, or you've got A hat is the gauge transform?
What have I? So I guess yeah, A is the original one, and I'm transforming it into A hat. Oh no. So yeah. I know.
So the second A hat should be
this is an A. Yeah. You're right.
Thanks.
Yeah.
Okay.
Yep.
And right, and then the rest next follows. Yep. And were you asking about why in the second line back, sigma inverse D sigma is a Lie algebra valued one form?
Yeah, well, I guess it's kind of this notation for me, at least for especially for when I have a principal bundle, it kind
I'll
of
tell you why it works.
Okay.
So if you put X into that potential one form sigma inverse D sigma, then sigma is a map from the manifold to the Lie group. You've already said that.
Yep.
So D sigma of X is a map from tangent vectors to
the algebra value.
To tangent vectors to the group at sigma. Correct?
Isn't it? It's a D sigma as a map.
D sigma of X is a tangent vector on the group. at sigma.
That's right. Yeah, that's right. I see. Yeah.
And sigma inverse on the left treats that vector at sigma as a left invariant vector field and maps it to the identity.
Yep. Okay.
And the standard way of representing the Lie algebra of a Lie group is the tangent space of the identity.
Yep. That's okay. Okay, that makes sense.
Okay. Yeah.
Yeah. And so now, I mean, this is the transformed equation, and what we're trying to solve is that d star of that equals 0. So the equation for the gauge transformations is d star sigma a, sigma inverse a sigma plus sigma inverse d sigma equals 0. But for this openness condition, we're trying to solve this in particular, where d star sigma inverse of a rho plus lambda sigma plus sigma inverse d sigma equals 0. And we're trying to solve for sigma, for some sigma in the gauge group. Now, I'll just kind of say kind of the basic method. This is kind of similar to how you do like a nonlinear, when you try to solve a nonlinear equation, nonlinear elliptic equation, it gives you a nonlinear mapping between Banach spaces. And so you take a point, and then you linearize it, and then you have a corresponding linear elliptic PD, and then you can show that that is an isomorphism, and then you can use the inverse function theorem to get back a solution to your nonlinear equation. In this case is something similar. We consider the map F rho, which takes a element of the Lie algebra X and lambda, and then we look at d star of e to the minus x a, where this is the exponential map from the Lie algebra Lie group, ex plus e minus x a rho plus lambda e to the x. And what we do is you take this map, you linearize it, look at df at 0, and then show that it's an isomorphism. Then you can use the implicit function theorem to solve for x in terms of lambda, so provided that you use small lambda. We have small lambda, and to do that, you'll have to use the openness condition, the openness of the part C. Okay. And so once you've shown openness, then you've shown it's open and closed. You've shown it's non-empty. So then 1 is in U, right? So you can solve for. You find a gauge transformation of A that has those three properties. Okay. So, I mean, I think the main usefulness of this is that this theorem is kind of one of the main things you need to prove first before you can prove Uhlenbeck compactness. And also, there is an explanation in Uhlenbeck's original paper that I wasn't 100%, I didn't 100% understand, but it makes most, because you have to somehow patch these local gauges together to get a global gauge, and then show that it all works out properly. And then what you can do is you have your connection on your principal bundle. Then you can, as long as it has finite total curvature, then you can look at open neighborhoods of the surface and make them small enough so that the curvature is less than epsilon. And since this original integral we have, like this integral e f a to the n on 2, that's scale invariant. So we can scale that up to 1 and it will be the same. We'll still be less than epsilon. And then we can apply the theorem to get the d star a equals 0. And then Now the Yang-Mills equations, I believe they stay the same under gauge transformations, it appears. And so you can couple these two equations together and get an elliptic equation, which then you can use to prove, regularity results for Yang-Mills connections. Okay, I think I'll stop there.
So a question is showing that df of 0, 0 is an isomorphism. Is that pretty straightforward, or is that do you know?
I don't think it. No, I think it is straightforward. If you differentiate it, because actually, it actually would be quite complicated. I think if you didn't put a 0 here for the e to the x's, right? Because they don't commute. Because you could be x is if your group is SON or something, then they don't commute. So, but then it actually becomes quite easy to compute because you're evaluating it at 0. And then the operator you get has highest order term, which is the Laplacian. So yes, it is. I don't think it's too difficult.
So it's that property that the highest order terms in the Laplacian is basically what gives it to you, isomorphism. Okay. And what was the constraints in your theorem? Can you go back to the statement of the theorem?
Oops, too far.
Right. So the constraint on P is it's less than n.
Yeah, actually, the original theorem says A is not smooth. A is in W1P. And it also proves that if A is in W1P, then this theorem is true for P greater than or equal to n on 2 and less than n.
Yeah.
But in this case, actually, this theorem is true for P greater than 1. I've written less than n because the way I've done it, it doesn't work if P is equal to n. But it actually, this appears to stated in that survey article by Donaldson. It says that this is true for P greater than 1.
Right.
As long as A is smooth.
So the extension to instead of P being greater than or equal to n over 2, as in Uhlenbeck's original paper, the extension for P in the range you've said is due to Donaldson, or you said it was stated by Donaldson?
I think it's. I couldn't actually. When I was doing this calculation, I couldn't figure out where. I didn't look at the original paper too carefully to know exactly why you needed it to be greater than or equal to n on 2, but this is in the smooth case, so I think it probably was well known already if A is smooth that you can do this for P greater than 1.
Right. Yeah, it's the because you've got F is dA plus A wedge A, so first derivative plus quadratic term, you're sort of naively we're looking for A to be in W1, 2 intersect L4.
Okay.
But the Sobolev, if you constrain P to be greater than or equal to n over 2, or greater than n over 2, then the Sobolev embedding theorem and some other embedding theorem for LP spaces just gets you where you want to be. So yeah, so I've got no idea how it gets extended to the setting that you've got.
Yeah, I'm not sure. It's just it's not there's no details provided in the paper, but it says that apparently it is similar to how to do it. Maybe you just need to play around with it a bit more.
So you're saying there's no details given in Donaldson's paper, or which paper?
Not for P greater than or equal to n.
Right. Greater than or equal to n over 2. Oh, sorry.
No, n. So okay. This is all for P less than n. But for P greater than or equal to n, you obviously can't do this. You can't do this step here, any of these steps here.
Oh, okay. Yeah.
Does anyone have any other questions for Vishnu about the content of this theorem and its proof. All right, then in that case, let's thank Vishnu for giving us a wonderful talk. Also, thanks a lot to Peter for asking a lot of good and important questions there. All right, that takes us to the end of our seminar for this time. We do have one planned for 2 weeks from now, the 24th of May. We have Brad Wilson from University College London, who's agreed to talk to us about some of the work that Uhlenbeck did with harmonic maps. Given how our next speaker will be joining us from the UK, it's going to be a bit of a late one, so we're aiming to have this talk occur at 4 p.m. On the afternoon of Friday, the 24th.